last lecture in this unit. It's called What's the Hurry? It says, nature does not hurry, yet everything is accomplished by Lao Tzu. So the learning goals for this presentation are number one, that you be able to determine the acceleration from a velocity versus time graph. Now this is something that we already did in the investigation, but we're going to experience it again. We're going to look at velocity versus time graphs, and we're going to see if we can find the acceleration given a graph. We're also in the formula that you see here. This is the formula for acceleration that we'll explain a little bit later as we go on. But keep these goals in mind as you work your way through this presentation. Alright, so what we already know. From previous information, including units or the second and third lesson in this particular unit, we know that objects can change speed or velocity. Remember, a lot of times those two are interchangeable as long as there is no change in direction. As long as there's no change in direction, speed and velocity are the same thing. We know that when you step on a gas pedal, you'll accelerate the car forward. In other words, you will increase the speed. We know that stepping on the brakes will slow the car down. In other words, it will decrease the speed. Now, what we learned in the lab. We learned that the longer the time the ball was allowed to roll along the floor, the larger the final velocity. So you have a ball, and if it's allowed to roll down that ramp for a longer period of time, the longer it's able to roll, the faster it's going to be going. We also know that the ball accelerates down the ramp. So in other words, it gets faster and faster and faster as it moves down the ramp. Now, acceleration. Acceleration is the focus for this presentation. Acceleration is the rate of change in velocity, and it includes two parts, both magnitude. Now remember, magnitude refers to the number. So whenever you have something like a 10 or a 2, those are examples of magnitude. So acceleration is the rate of change in velocity, magnitude, or direction. Now direction means something like north, or to the right, or south, or something along those lines. So because acceleration has both has both magnitude and direction, acceleration is a vector. So we have to include both magnitude and direction when we report it. So you see vector right here. He's the famous guy from that cartoon. I just drew a blank on what it is. The SI unit is meters per second squared. So anytime you see something in meters per second squared, like gravity, it's an acceleration. Now, a lot of people think gravity is a force. In actuality, when we refer to gravity as 9.8 meters per second squared, we're actually referring to the acceleration due to gravity. Now, there's examples of acceleration. If you step on the gas pedal, you increase your velocity. If you increase your velocity, you've changed the magnitude or the number of your velocity. You've gone from 10 to 20. If you step on the brake, you've changed the magnitude of your velocity because you went from 20 to 0. So in both these cases, stepping on the gas pedal and stepping on the brake, you've changed the magnitude of the velocity. In other words, you've changed the number. You can also change the velocity by changing the direction, and that's accomplished by turning the wheel. You could be going 10 meters per second, turn, and be going 10 meters per second in the opposite direction. If you do that, there's no change in the magnitude, there's no change in the number, but what there is there's a change in the direction. If either the direction or the magnitude changes, you've had an acceleration. So we need to compare velocity and acceleration. Now the reason why we need to make this comparison is a lot of times people get these two things confused. So one of the things that they do have in common is the fact that they are both vectors, which means they both include both magnitude and direction. They are also both rates. In other words, they depend on how much time goes by. But they're very, very different other than that. These are the only two things they really have in common. This right here is the rate of change in position. We're going to say x is position. So it's saying, okay, I was here and I was here. How long did it take me to get there? So it's the rate of change in position. Velocity is measured in meters per second. Sometimes we think of velocity as speed, and they are the same as long as they're in the same direction. And we represent velocity with a v. This represents how fast you're going. Now, acceleration, on the other hand, is very, very different. It is the rate of change in velocity. Okay, the rate of change in velocity. So how much are you getting faster, or how quickly does it take you to change your speed? Okay, for example, some cars have an incredibly high speed, but it takes them a very, very long time to get there. Some sports cars, though, can go from 0 to 60 in 3 seconds. That's a rate of acceleration. The unit for acceleration is meters per second squared. Okay, you see how they're different right here. They're different units, and that's going to be the key to figuring out what something is. There is no equivalent for acceleration. There's no like, oh, it's kind of like speed. Okay, and this is how much or how quickly can you change velocity. Very different quantities. Now, if you have a velocity versus time graph, which is what we generated in the lab, you can find the acceleration by looking at the slope. Now remember, when we talk about finding the slope is the rise over the run. Okay, the slope is the rise over the run. So what you need to do is you need to pick 2 points. Any 2 points along this straight line graph, and you need to say, okay, y2 minus y1 over x2 minus x1. That's how we're going to calculate the slope. Now, what is the dependent variable according to the graph? Now remember, there are 2 different variables whenever you graph them. You have the independent variable, which is on the x-axis. The reason why it's the independent variable, it's the one that exists independent or without the other variable. You have the other one, which is the dependent variable, and that's always on the y-axis. And that's the one that's going to depend on the original one. So for example, this is very similar to the lab that we did. The velocity of the car at a certain point depends on how long the car was able to roll down the ramp. The longer the car was able to roll down the ramp, the greater the velocity. So velocity depends on the time. The time does not depend on the velocity. So that's why we have our dependent variable and our independent variable. Next, it says, what is the acceleration of the car shown to the right? So remember, whenever we're looking for the acceleration, what we always do with a graph is we check the axis. We have velocity and time. Since this is a velocity versus time graph, the acceleration is the slope. But you always need to check these axes, because sometimes this we've already done could be a distance, or it could be position, or something along those lines. It could be something different. It's not in this case, but I need to make sure that I check before I just assume that I'm supposed to find the slope. So I need to find the slope. I'm going to pick 2 points. It doesn't matter which 2 points you pick on this line because there's a straight line. I'm going to pick the 2 easiest ones to read. The 2 easiest ones for me to read are this and this. And the reason why is because they have exact values that I can see as I go down. I don't have to estimate and say, oh, I think that's pretty close to 16 or 17. I want to choose the ones that are exactly on lines if I can. So the 2 points that I'm going to choose are 0, 5, because x is 0, y is 5, and then 5, 20. So these are the 2 points that I pick. I would get the same value if I picked any of the points along the line, as long as I read the graph correctly. So now with these 2 points, to find the slope is the rise over the run, or 20 minus 5 over 5 minus 0. The y's on the top, the x's on the bottom. When you do this, you get 15 over 5, which simplifies to 3. Now 3 is the magnitude of the velocity, or excuse me, the magnitude of the acceleration. But we need to make sure we put a unit with it. And if you look, what I did is I took the top number. The top number was in meters per second, and then I divided it by time, which was in seconds. So you have meters per second per second. Well, when you have 2 per seconds, you can just write it as meters per second squared. The next example is a little bit tougher. It says a car starts at x equals minus 20. So here's 0. And the car starts at minus 20. And then it moves according to the graph. It says, what is the final position of the car? Now, this right here is going to be the final position of the car. It's going to be at 5 seconds. Now what I want to know is I want to know where the car is. Well, what I want to do is I want to figure out how far the car has actually moved. Now, in order to figure out how far the car has moved, we have the speed equals distance over time formula. But this won't work in this particular case because if I were to use a time of 5 and a speed of 20, well, the car is not moving at 20 meters per second for the whole 5 seconds it's traveling. So instead, this is truly an extension question. I need to figure out a way to multiply the velocity times the time. And what you can do is you can look and see, okay, well, if I do that for the graph, what I do is I get a weird shape that looks like this. So in other words, if I can find the area under the line, it will tell me the displacement. Well, the problem is that's no shape that I really know, but what I can do is I can break it down into two shapes. I can find the area of this rectangle and the area of this triangle. When you take that, you'll have the total area under the line, and that represents the displacement, or how far you've moved. So I find the area of the triangle. I have 5 times 15, which is the height of the triangle. So 1/2 of 5 times 15. Okay, and then I also have, that's 125. And then I also have the area of the rectangle. The rectangle is 5 by 5. So 5 by 5 is 25, which gives me, when you add those two together, the total area is 150 meters. What that represents is that represents how far the car has moved from where it started. Well, if the car starts at -20 and moves 150, it doesn't end up at 150 because it moved 150 from -20. So if you had 150 and it started at -20, this would represent that it traveled 130 meters. This is a very, very, very difficult example of how to use a velocity versus time graph. But all you have to do is find the area like we talked about and then add it up. Next, we can talk about acceleration. There's a couple of different ways that you can measure acceleration, but all of them are what we call indirect. There's only certain things that you can measure directly. Instead, everything else you have to measure several different things and combine them together. And that's what an accelerometer does. An accelerometer is a device that's used to measure acceleration, and they're commonly found in smartphones, Wiimotes, PlayStation 3 and 4 controllers, digital cameras, and lots of other navigation devices. In fact, usually your phone has roughly 3 accelerometers because it wants to be able to measure it in all 3 dimensions. Is it moving up and down, side to side, or is it moving back and forth? Okay, all of those things allow them to measure the acceleration and kind of give you the ability to do them, manipulate your phone in certain ways to play games, to see if you're driving, or something along those lines, to track your movement if you're working out. But accelerometers are found in all of these devices. This right here is the accelerated motion equation, and this is the version of the equation that we're going to stick with for this presentation. So you have A, which stands for acceleration. Acceleration, we've already talked about, is the rate of change in velocity and is measured in meters per second squared. Now, so far we've only talked about velocity before today. And this has a velocity, it's a v, but it's got a little f with it. A lot of times when you have a little f, we refer to this letter, this thing, as a subscript. That subscript is a way to further define the original variable. So this is not a v and an f. They're not two separate things. It's a v, an f that describes the v. So v is still a velocity, but because it has an f with it, it stands for final. This is still a velocity, but because it has an I, it stands for initial. But they're both measurements of velocity. They both are measured in meters per second. They can both be measured with radar. They're just different velocities. Next, you have the time. The time is the interval between events. A lot of times you will see it as delta t. Sometimes you will just see it as t, depending on the book or depending on the worksheet. So this says, what does delta mean in an equation? Remember, delta always means change. So when I say delta t, that would refer to the change in time, or how long it takes for something to occur. But another way of thinking of delta, delta also means final minus initial. So if you look at our equation, we have acceleration equals final velocity minus initial velocity. Well, that's the same thing as delta. So a lot of times you may see the equation written as a delta v over delta t. That is the exact same thing as a equals vf minus vi over delta t. They're the same thing. Delta means change, or final minus initial. Next it says a car accelerates, okay, this is a keyword, accelerates, from 6 to 15 in 3 seconds. So because I'm trying to calculate here, I'm going to use the guess method. Remember, the guess method means we have to have our given. The information that's given to me is I have a velocity that is 6 meters per second. I have a velocity that's 15 meters per second. I have a time that's 3 seconds. Now what I need to do is I need to use my context clues to decide which one of these is initial and which one is final. Now if you read it, it says from 6. That lets me know that that right there is the initial. To 15, that lets me know that this is the final. So I have an initial, I have a final, and now I can solve for my unknown variable, which is my u, unknown. The next thing that I do is I write the equation. The equation that I have is a equals vf minus vi over delta t. Now I plug my numbers in. I would get 15 minus 6 divided by 3. Now one of the things that you need to be careful about is how you enter this in your calculator. Please make sure that you go ahead and do 15 minus 6 first, and then hit enter, and then divide by 3. If you were to hit 15 minus 6 divided by 3, it would take 6 and divide it by 3 first, and then subtract it from 15, and that's not what you want. So make sure you do the numerator, or the top, first, and you would get 9 divided by 3, which would give you 3 meters per second squared. The next example says determine the acceleration of a boat that accelerates from 10 meters per second to 30 meters per second over the course of 2 minutes. So this one is a little bit more difficult. I'm still looking for acceleration. I still have this 10 meters per second, which I know is a velocity, 30 meters per second, which I know is a velocity, and I still have a time. So I'm going to do my given. The given information that I know that my initial velocity is 10 meters per second. Once again, I know it's initial because it says from 10 to something else. I know my final velocity is 30 meters per second. I know the time that it takes is 2 minutes. Now you should know by now that 2 minutes is not a standard unit for time. So I need to change that or convert it from 2 minutes to something else. And what I can do is I draw my line. In 1 minute, there are 60 seconds. So instead of expressing the time as 2 minutes, I would be better served by writing it as 120 seconds. Now that I have my given, I know my unknown. My unknown is acceleration is equal to question mark. Now I can use my equation. My equation is a equals vf minus vi over delta t, or t. Now you can plug in your numbers. You would say a is equal to 30 minus 10 divided by 120. Please make sure that you do 30 minus 10 first, and you get 20 divided by 120. And when you put that into your calculator, you get something along the lines of 1 over 6, or if you go ahead and multiply it out, you get something along the lines of 0.167 meters per second squared. Now it's really important that you spend some time practicing these equations and plugging them into the right place, and then also making sure that you can use your calculator to get the right answer.